What you'll see today, physicists managed to teleport quantum information between two photons, taking another concrete step toward the so-called quantum internet. In the United States, a regulator cleared the first human test of a brain implant that promises to give voice back to people who can no longer speak. China, for its part, put a humanoid robot to walk 106 kilometers on real streets, autonomously, and made it into the Guinness records. And there's also a warning that shines a light on the most overlooked point of this new era. The physical strength of these robots can be so great that if something goes wrong, the risk is no longer theoretical. Before we continue, if you want to keep up with everything happening in the future of technology, subscribe to the channel and turn on notifications so you don't miss anything. Let's get to the video. Think about the idea of someone being able to communicate again without moving their mouth, their tongue, not a single muscle. It sounds like science fiction, but now it has officially entered the human testing phase. In the United States, the FDA authorized a speech-focused brain implant to be evaluated in volunteers for the first time. The project puts paradromics in a select group of companies at the forefront of brain-computer interfaces, and the reason is simple. This isn't a gadget, it's technology touching one of the most basic parts of human life: communication. At the heart of the study is Connect One, running on the Connexus BCI platform. Physically, it's a titanium implant with more than 400 ultra-fine platinum iridium electrodes. These electrodes are so thin they're below the thickness of a human hair. Their job is to record neural signals at a data rate high enough to capture the activity of individual neurons. How does it go into the body? Surgery places three main parts: the cortical module, an internal transceiver, and an extension cable, all under the skin. The electrodes sit just below the brain's surface, aimed at the motor cortex linked to movements of the lips, tongue, and larynx. In other words, exactly the region associated with speech. The captured neural activity follows a well-defined path. It travels through a subcutaneous cable to a transceiver installed in the chest. From there, the data is sent wirelessly via an optical connection to a second module, now external. This external module receives power by inductive charging, as happens with some modern smartphones. Then comes the magic that is, in truth, heavy engineering. The system sends the information to a small computer that uses advanced language models and artificial intelligence to decode the patient's intention, what they tried to say. The output can be text or synthesized speech, according to each person's preference. The trial will start small and controlled, only 2 participants. Each volunteer will receive an implant 7.5 millimeters wide, inserted about 1.5 millimeters into the motor cortex. The goal is ambitious. For the first time, a fully implantable interface will try to generate synthetic voice in real time, and it will do so using past recordings of the patient's own real voice as the basis. And it doesn't stop there. The study will also observe whether the chip can recognize imagined hand movements, which opens a second front, controlling a cursor and restoring some digital independence for those who have lost almost all traditional forms of interaction. This chip story shows technology as an extension of the human. Now flip the switch from the human brain to the robot's brain. Because while AI advances in text and voice, there's an entire world trying to place intelligence inside bodies that need to work in the real world. No tricks, no controlled set, no margin for error. When Boston Dynamics decides to speak frankly, it's worth paying attention. In a sector addicted to quick promises and flashy demos, the company, now controlled by a South Korean group but operating and based in the United States, presented a rare analysis of the real stage of humanoid robots. And the message was direct: the industry would still be in phase 1. Behind the new Atlas, now fully electric, Boston Dynamics seems to adopt a far more cautious philosophy than some competitors who talk about months of continuous operation as if the hard part were already over. One of the names cited in this line of thinking is Rodriguez, a former MIT professor associated with Boston Dynamics, who describes a robot's life cycle in 3 stages: build and make it reliable, get the machine to work without failing all the time, face the customer's world. When the robot leaves the lab and you discover almost all your assumptions were wrong, scale to thousands, mass produce and handleware and long-term issues. His diagnosis pulled no punches. All humanoids, without exception, would still be stuck in the first stage. Here, a key detail comes in. The automotive sector appears as the perfect lab. Not only because it's a huge market, but because that's where physical manipulation pushes the limit. Extreme precision, difficult tasks, and endless variation. Rodriguez gives an almost symbolic example. Pick up a loose screw inside a bin, orient the part in the air, and fit it into a car body while the robot braces itself with the other hand. If a machine masters that, it masters almost anything. And that's exactly the reality of automotive lines. Factories that produce 5 different models with thousands of part variations. The robot needs to understand the organized chaos of production. But the deeper shift may be happening inside the software that runs this body. The old layered logic, a kind of processing pyramid, would be replaced by end-to-end neural networks. The expression end-to-end, which Hyundai uses, sums up this transition. It's no longer about writing perfect code. It's about building systems that make mistakes, learn, and keep getting better. While some companies turn any advance into marketing, Boston Dynamics seems to bet on slower maturation. And here a question lingers. Is this a conscious strategy or a limitation in capability? Because looking at the market, there are companies in the US and China that seem ahead in certain areas, perhaps already living something closer to Phase 2. Even if the industry is at the beginning, there's a question that won't wait for the future to arrive. What happens when a humanoid robot, with machine strength, makes a mistake near people? And this is where a complaint changed the tone of the debate. A lawsuit in California brought the issue down to earth. Not AI as software, but the physical power of these machines. The plaintiff is Robert Grandel, former head of product safety at Figure AI. According to him, he was fired a few days after warning leadership that the company's robots could cause serious injuries. He described a specific episode. A malfunction allegedly caused a humanoid robot to dent a refrigerator's steel door by 6 millimeters, a blow that, in his view, would have enough force to crush a human skull. In other words, this isn't a shove. It's real mechanical energy. The company disputed the accusations. In a statement to CNBC, a spokesperson said Grandel was let go for poor performance and called the allegations false, promising to fight everything in court. The lawsuit seeks damages and a jury trial. The whistleblower's attorney, Robert Ottinger, argues that California law protects employees who flag safety risks, which could turn this case into one of the first major legal showdowns involving humanoid robots and public safety. Grandel claims the core problem is the rush to reach the market with safeguards pushed to the background. And this is blowing up at a moment when Figure AI is experiencing very rapid growth, which naturally increases scrutiny. Are the safety protocols scaling at the same pace as the breakthroughs? The case raises a red flag in a sector that for a long time focused its fears on digital AI and overlooked the impact of machines capable of causing physical harm. And this isn't a made-up fear. Robotics already has a record of serious episodes. There's the widely reported case at a Volkswagen factory in 2015, plus an older incident in Japan in 1981. And more recently, a Tesla engineer was allegedly attacked by a faulty robotic arm at the Austin Gigafactory, an episode that drew attention both for its violence and for the weight of the Tesla name. As humanoids leave the lab and enter human spaces, this lawsuit against Figure AI turns an abstract concern into something concrete. The discussion has arrived in real life. Now we leave brute force and turn to an old dream, transmitting power wirelessly, not just across a room, but at space scale. That idea so often associated with Nikola Tesla, sending power through space, is taking practical shape. Starcatcher Industries achieved a result that made news for a simple reason. It broke a record inside a DARPA-linked challenge, showing that wireless power transmission can become a real component of space infrastructure. The test delivered 1.1 kilowatts of power directly to the Kennedy Space Center, using only commercial components and an array based on solar panels. That's a jump over the previous 800-watt record, set the prior year also in a DARPA context. And what's most interesting is how this story has old roots. Back in 1941, writer Isaac Asimov imagined orbital solar collectors sending energy to Earth by microwave. Decades later, engineering is starting to brush up against that literary glimpse. The logic has always been enticing. Panels in orbit collect almost continuous light. No night, no clouds, no atmosphere in the way. The problem is that building solar megastructures in vacuum is still far off. But there's another, much more immediate bottleneck: satellites and spacecraft have limited power. More power usually means more panels, more mass, more cost. That equation has stalled a lot of things for years. Starcatcher is trying to change the game with a technical choice. Instead of microwaves, it uses a multi-band optical laser powered by a solar panel array. This laser is precisely tuned to match the customer's solar panels. In practice, it's like concentrating light with a giant magnifying glass, boosting efficiency without forcing a redesign of the satellite's hardware. The latest test involved several types of panels precisely to pave the way for the first in-orbit demonstration, planned for 2026. That stage is critical because only it validates whether the concept works where it truly matters, in the space environment. Now, I want to return to humanoids because there's a quiet contest underway. And it isn't measured by pretty videos, it's measured by repetition, cadence, and numbers. The question is straightforward. What matters more in the robot race? Impressive acrobatics, or repetitive work done until it becomes routine? The answer began to appear in a decidedly unglamorous place, in Georgia, inside a GXO Logistics Distribution Center. There, Agility Robotics' bipedal robot Digit hit a milestone that says a lot about operational maturity. More than 100,000 boxes moved. It's a simple number, almost dull, and that's exactly why it's powerful. In a market full of prototypes that look amazing but rarely do real work, this kind of milestone is born from the real world, from the last meter of material handling. While autonomous mobile robots carry things along more predictable routes and industrial arms dominate fixed tasks, the humanoid form steps in where nothing is fully standardized. Digit picks up, carries, and repositions. It fills the gap that, for a long time, only humans solved. This milestone is also part of a broader GXO test that evaluates a robotic workforce with other machines, including systems from companies like Apptronic and Reflex. But by publicizing such objective numbers, Agility gives the impression of being a few steps ahead in validation. And there's a timing detail. It came a day after rival figure announced that its F.02 robots handled around 90,000 metal parts at BMW. Agility's response wasn't online snark, it was volume. 100,000 against 90,000. In a contest full of public accusations and even predictions of bankruptcy, there's a kind of argument that doesn't need to shout. It simply stacks up work and lets the numbers speak. And while the public watches this rivalry within the US, pressure is growing on the other side of the planet. China's UB Tech is already talking about mass deliveries of industrial humanoids, shipping hundreds of units to automotive factories. The board is shifting, and the question that defines the winner is evolving too. It's no longer, can the robot do it? Now it's, how long can it repeat that without stopping? If the future will favor the most durable, what happened in Georgia may be only the start of a new phase. Now the setting changes completely. The factory floor is out. Cutting-edge lab is in. Because an experiment with photons just solved a key piece for long-distance quantum networks. The scene seems impossible. Two photons are born in different places from distinct sources and still manage to synchronize their quantum states so that the information from one jumps to the other, with no copying, no amplification, no classical shortcuts. That's what a team at the University of Stuttgart managed to demonstrate. The impact is big because it tackles a central obstacle in quantum communications. In optical fibers, individual photons are gradually lost along the path. And since quantum information can't be cloned, a dilemma appears. How do you extend the connection without destroying the data? The long-standing theoretical solution is the quantum repeater, which refreshes the state via quantum teleportation. But that imposes an almost cruel requirement. The photons involved need to be practically identical, and two separate sources rarely deliver that. That's where quantum dots come in. Nanoscale semiconductor structures capable of emitting photons on demand. The Stuttgart team worked with the Labre Institute, which built quantum dots so similar that their differences were almost unmeasurable. According to Peter Möckler, this was the first time quantum information was teleported between photons produced by distinct quantum dot sources. And the result wasn't symbolic, it was functional. with a success rate a little above 70%. This advance adds to a previous experiment by the same group, which had already demonstrated maintenance of quantum entanglement over 36 kilometers of fiber crossing Stuttgart. Now, with photons from different sources truly talking, the fundamental pieces of repeaters are starting to fit together. The final target is clear: build a quantum infrastructure that integrates with today's fiber networks and becomes the backbone of what many call the quantum internet. If victory in the lab is synchronizing photons, victory in the real world is surviving the unpredictable. And that is exactly what a robot just did in China. Almost no one expects a humanoid robot to walk across an entire city. Now imagine doing that across 2 cities, on a real route. That's what happened between Suzhou and Shanghai, in a journey that became a quiet milestone with huge implications. Shanghai-based J-Bot took its Expedition A2 robot out of the controlled environment and put it on the street. The machine covered 106 kilometers continuously and autonomously, with no one piloting it, only its onboard AI managing balance and decision-making. The feat was recognized by Guinness as the longest distance ever walked by a humanoid robot. And it wasn't on a treadmill or a perfect corridor. It was real streets, with all the mess of the real world. The route put the A2 on surfaces that are hard for any balance algorithm: uneven asphalt, slippery tiles, and even those tactile paving strips used to guide people with visual impairments. And a considerable portion of the walk happened at night, when even for humans, the environment is less forgiving of errors. But for a machine, that doesn't change the duty. It has to keep going. But the most interesting point wasn't just the robot walking. It was how it handled power without dying along the way. The entire journey happened without shutting down thanks to a hot swap battery architecture. While many projects bet on integrated structural batteries, J-Bot chose swappable modules. Human technicians replaced the power module while the robot was still on, sustained by an internal reserve that kept the system alive during the swap. It may sound like a detail, but it's a direct attack on automation's nightmare: downtime. If you can swap energy without shutting off, you open the door to continuous work cycles, potentially 24 hours. At the end of the journey, on Shanghai's Bund, the A2 arrived without significant damage, just natural wear on the rubber soles. The patented actuators of the power flow system endured hundreds of thousands of load cycles without signs of fatigue. And here are the specs that give a sense of the feat. The robot is about 1.75 meters tall, weighs 55 kilograms, and has more than 49 degrees of freedom, designed to operate in the same workspace as we do. The 106-kilometer record isn't just a number, it marks a boundary. When mechanical endurance stops being the main obstacle, the challenge shifts somewhere else, to the AI brains that need to turn this body into a truly useful worker. If you made it this far, you clearly enjoy this kind of technology. So tell me, in the humanoid race, what matters more to you? Rare skill, doing hard things once, or tireless repetition, doing the same thing thousands of times without failing? And one more, if the feet of these robots already endure journeys like this, how long do you think it will take for the artificial intelligences inside them to keep up with the body, in practice, in day-to-day work? If you liked the episode, leave a comment, hit like, and subscribe so you don't miss the next updates. And click one of the suggestions on the screen, because I'll see you in the next video.